Camera on. Okay.
Good morning, Chloe.
Good morning. Okay, good morning, everyone. I want to make sure our presenter has all the time he needs, so we'll get started. So thank you all for being here. Uh, so today we will be having Marcel present chapter 6 on functions. I'm very interested in this because I write a lot of functions and I never really know what I'm doing, but I just figure out a way to make them work. So I'm excited to learn more about how they actually work. Take it away, Marcel.
Hi everyone. I'll share my screen. You should be able to see that. Right?
Yes.
Okay, so I'll just go through the textbook section here and try my best to explain this advanced R chapter in functions. So how many people have used the functions before or written a function before? You can, I guess, raise your hand in the, and I can see the chat. Okay, good. Yeah, so we'll skip this quiz because the quiz is for evaluating whether you can skip the chapter. So we'll go straight to the outline and go over the objectives of the chapter. The first objective is to describe what is a function, what are the components of a function, and there are some exceptions to the rules, like primitive functions that are implemented in C, not in R. And then we'll look at the strengths and weaknesses of the way you would write a function as you would see it in R code. And third bullet point here shows you this talks about this fancy computer science term called lexical scoping. It just, if you've worked with functions already, it's pretty intuitive, but here we'll make that a bit more explicit and talk about the rules of lexical scoping. And then for the fourth bullet point, we're looking at the arguments of the functions themselves and when are they evaluated, and we'll talk about the lazy evaluation of these arguments. And then we'll we'll talk about the dot notation in a function, and what it does, and some peculiarities about that notation. So I think we're covering a lot of material, so I'll try my best to sort of skip the sections that may be a little bit too much, I guess, playing around with the functions that Hadley, the examples that Hadley shows, but and more about how you would use these, or how would you deal with these special situations. So, and the last two bullet points are for ways to exit a function, define an exit handler, and what triggers it, and then some prefixes. So let's get started. The way we define a function is by its components. You have an argument, the list of arguments in that make up a function, the body, right? That's the code that the function wraps, and then the environment. So the environment is the isolated environment where these inputs get manipulated, right, by the body, right, the code that's in the function. And of course, there are exceptions. These primitive base functions are implemented in C, and in R, functions are objects, right? Everything in R is an object, including functions, and that's a feature of the R language. So let's talk about the three major components. The formals is another term for the arguments that make up a function, and the body, which is the code inside the function, and the environment, which is the how the data structure that tells the function where are these values that you're referring to in the arguments. I would also say that you have those three parts, but you also have a name, right? As we work with R, the name is important, right? And sometimes you could have, ideally you would have one name for one function, but sometimes functions may have the same name but a different body, for example. So that is possible, and there are ways to be more explicit about what function you're referring to. So the formals and the body are specified when you write the function, right? And the environment is implicit, and that's where you define the function, right? So in this session here, we're using the global environment, right? So in this example, right, where I'm defining the function is in the global environment. So it will, if I run this, you'll see that if you look at your environment tab, that function has been added to the global environment, right? So if you're developing an R package, right, this would be different, right? Your function would be defined within the package namespace, right? The entirety of all the functions that are in the package. And so you define the function, right? So a lot of you have already worked with functions, but you use the arrow or you could read it as gets, right? F02 gets the function keyword. You specify the arguments, and then you use the curly braces to specify the body of the function, right? The curly braces are optional, but highly recommended, right? You can define a function without the curly braces, but you should only go that route if you have a short and small function. So most of the time you'll be using the curly braces to tell R, this is where the function body starts, and this is where it ends. And then you have these sort of meta programming functions that allow you to pull out the arguments of a function that has been defined, right? So if you do formals, as you can see on the left here, on the right, we have the two arguments that are part of the function. You can also use body, and to be honest, I've actually never used these. Well, I have never used body before. It's interesting to see it. Most of the time, if you want to see the body of the function, you just call the function by its name. So you do something like F02, and that gives you how the function was defined. So it gives you the call, not necessarily the body, but you get the rest of the call that created that function. And then you have the environment, and that would give you the environment where the function is defined. And since we are running this interactively, it's the global environment. So I think this diagram, I guess I can run this, and I guess I can show the diagram in the yep. So this is what Hadley's diagram would look like. You have a function that's enclosed with two variables inside of it, and those are the arguments. So you want to think of a function like that. Most of the time, you're working with the inputs, but you also have to be aware that for anything that R doesn't find inside the function, it's going to look usually immediately before or outside of the function for the for any other things that are not defined in the environment. So in this example, it seems pretty trivial, right? X plus Y. We do have X and Y in the function environment, but there's this plus sign, right? This is actually a function itself that's not defined inside of the function. So R recognizes that and looks outside of the function to find what does this cross mean, and what does it do? So it will find that function and use it for the two arguments. There are other ways to pull up the attributes of a function. Some functions, especially if you are working with some API packages or like web packages, functions can have a number of attributes, and sometimes these are like auto-generated, but you can pull up the attributes of a function, and this src ref just is another way to obtain the function call that created F02 function 2. So now let's talk about some primitive functions. These are the lower level functions, and by lower level, I mean their implementation is closer to C, or to the way it was implemented is in C directly. So you can't manipulate them exactly the same way as you would for a function that's been defined in either the global environment or in a package. And these have this primitive function call in their definition because it's telling R to run the code, the C code, in the background and return the output of that command. So you either have built-in or special types. Special is usually referring to some kind of symbol like the bracket, and built-in for any other functions. And one thing about these is that the formals, the body, and the environment all return null, right? These are not your typical functions. These are primitives, so they don't have the same body and environment formals as a function that defined in the global environment. So primitive functions are only found in the base package because they're implemented in C in the base package, and they're harder to write. So yeah. What we're mostly working with are the first class functions, and these are functions that are named, right? So you not only have this function keyword, but you also have a name, and ideally a single name for every function, but you can have multiple names, right? And Hadley's diagram here shows a sort of the name pointing to the object, right? In R, we have some sort of allocation here and a variable inside the object. So, and then we have several function calls actually inside of our own function, right? So you have sign, you have the division, and then you have the caret, and yeah. So one good thing about R is that you don't really have to tell R where the sign function is, where the division function lives. It sort of goes out and finds it and makes writing code in R much easier. So those are named functions. These are first class functions, but you can also have anonymous functions, and these are useful if you're using them like one-off, for one-off operations. And for an example here is the lapply. Lapply uses a function as an input. So our first argument here is the mtcars data set. It's a data frame, and the function input can be a function that you write ad hoc. So in this case, you want to get all of the unique values in a particular variable, right? Because mtcars is a data frame, which is a derivative of a list, or you can think about it as a structured list, and it's column-wise, right? So if you lapply on a data frame, it's going to look at one column at a time. So you'll have the unique values of that particular column. The first through, it looks at all of the columns, right? So it'll go and do unique on those columns, and then the length. So you're looking at how many unique values are there in each column. I guess that's the question that you would be answering with this line of code. And then filter also accepts a function, right? Capital F filter. And it's good for, say, if you have a list or a data frame and you want to subset that data frame by a certain condition, you can do that with the filter function. And generally, the first argument will evaluate to a logical. So you're looking at, maybe your question is, what columns in empty cars are not, or give me only the columns in empty cars that are not numeric. And you would use filter to get the answer to that question or command, right? So these are anonymous functions, right? They have no name. They're just used for the purposes of that operation, and then they sort of don't get they're ephemeral. They don't have a name, so they serve their purpose, and that's it. You can also use integrate, which will tell R to find the integral, the function for the range of values. And then the final option is to put functions in a list. So if you have a set of functions that you want to run on your list or data frame, you can have a list that would sort of organize all of your functions that way. So here we have a list with two elements, half and double, right? And half corresponds to a function, x divided by 2, double, x times 2. So you can do funds $ double and then a 10, and that would give you 20, right? So, and in R, these functions are often called closures. So that means that's just the fancy term for a function. And it's good to know the terms that R uses, because most of the time we'll be confronted with an error that's using those exact terms. So it's good to be familiar with those terms. So generally, when you invoke a function, you use its name, right? And you open parentheses, and then you provide the input arguments, right? Sometimes the arguments are not named, so you do mean 1 to 10, but you could also say mean x 1 to 10, and then na.rm equals true, right? But sometimes you may already be working with the arguments as a data structure. So for example, you might have these arguments as part of a list from a previous operation. So you can, one nice trick to use is the do.call function to call that function with a list of arguments. And this is pretty handy. You can call the mean function on the arguments, right? The list here is, first element is the x, right? The numeric vector. And then the second element is na.rm equals true. Notice that na.rm is named, right? They can be named, or I believe they can also be positional without names, and that should still work. So do.call is sort of a different way of calling or invoking a function, which may come in handy if you're already building up to the arguments of that call from different from previous operations. So let's look at some of these exercises. Given a name like mean, match fun lets you find a function. Given a function, can you find its name? So this doesn't really make sense, right? If you have a function, most of the time, when you're working with a function, you'll have a name. If you don't have a name, then there's no way to know what function you're looking for, really, right? So, and I guess I have the solutions here. We can look at those. So the solutions here give an example. Well, there is no one-to-one mapping between functions and name. A name always points to a single object, but an object may have 0 or 1 or many names. So in this case, this function doesn't have a name. So if you have a function, it's just an anonymous function. But say you give it a name, right? And then you can have derivatives of this function or copies of the function with multiple names, and you can imagine as Hadley would draw it, right? The object function with f1, f2, and f3 all pointing to the same object, right? So, I mean, this is not something that you would typically do. Ideally, you would have one name for one function or operation so that there's no ambiguity. And actually, I've never used match fun before, but I do note that it is used in lapply, and that was actually new to me because I've never used that feature of lapply. So I guess we can take a look at that, and in our session here, let's look at the lapply. And you can see that there's this match fun in the first line of that of the body of lapply, right? So whenever I call lapply, I'm always providing a function, but there is an option to provide a name or I guess just for the purposes of this example, I'll do 1 to 10 and do mean in quotes, and that will actually work, right? Because of that match fun. The thing that match fun is doing, it will go out and look for a mean function and use that on each element of the input vector, right? That's strange. I wouldn't recommend using that because you can have a mean of, say, letters. There can be collisions, right? And if you do mean, like how do you know what mean is referring to here if you're using the name, right? And this is especially problematic if you're doing something like a function, because that's more what R will find and do like stop. This is an error. right? And then you do lapply mean, and it will find this mean function, and I think, yeah, it'll try to use that mean function and see that there are no inputs to the mean function. So if you're trying to give it an input, which is 1, it'll give you this unused argument error message. Right. So I would advise against the 2 things here. Name collisions, right? You don't want to use the same name when you're creating your variables or functions for an already established function, especially in the base package. And then, yeah. And you want to,
Marcel,
yeah,
in this example here, you're going to get an error whether or not you put the mean in quotes. Also, if it's not in quotes, now that you've redefined mean as a function.
yeah. This will go, lapply will go out and find this one. And if I added the dots here, it'll say, this will go in there and then it'll give you this error instead of the unused argument, which was what I was trying to,
I see.
show. So yeah, avoid name collisions and try to avoid the match fun functionality of lapply. I always use the function itself. And if you really want to be more specific, you would do base mean, and that would be the ideal scenario, where you could have something like a mean defined in the package or in your global environment, but because you said base mean, it will know what you're referring to and use the right function. Right, so for number 2, we have 2 function calls here for anonymous functions. Which of the 2 approaches below is correct? So if you have an anonymous function, it's always good to use I tend to use the curly braces to sort of delineate where it starts and ends so that it's not ambiguous. But in this example, it's purposely written as it's pretty ambiguous, right? So if you run this line, R will think that this is part of the body, 3 parentheses. And R will accept it, right, until you try to run the function, and it will know that 3 is not a function and will give you an error, right? So, but if you want to, I guess, evaluate the function and call it, right? Maybe these parentheses were meant to call this anonymous function in the same line, which is a little bit confusing, and that's why I would recommend using the curly braces. But the first step in this second call here defines the function, and it's a function that takes an x as an input and returns a 3. So by adding those parentheses, it tells R this is the definition, and then the following parentheses tells R to call it or invoke it, and that will give you the 3. So which of the 2 approaches below is correct, right? The second one works, but I would rather use the curly braces to avoid that ambiguity. And the rule of thumb here is that the anonymous function should fit in one line, so that you shouldn't need to use the curly braces. But it's just a rule of thumb, and I prefer to use the curly braces. Yeah, I hardly ever not use the curly braces for a single line function, but it also comes down to style. So yeah, and some anonymous functions can have multiple lines. It depends on what you're using it for. But if you're writing an anonymous function that has multiple lines several times, if you keep on using that anonymous function, then it's a good idea to create a first class function and use that instead, especially if you are testing your code, right? Which everyone should be testing their code. It's better to have a function with a name that you can test rather than an anonymous function, which is harder to test. So what function tells you if an object is a function? There's the is dot function, and how can you tell if there is if that function is a primitive function? So R has is dot primitive. And then there's this example where you can list all of the functions in the base package. And I think this is it's nice to go over and sort of do this on your own, I think, but I don't see ourselves using this very often, like mget or any of those functions are hardly ever used. And if, yeah, in our code or in analysis code, right? But for the example here, I think they just want you to be able to manipulate a list and filter using the is function. So I think I'll skip this part because there are multiple, unless someone has like a preference for any of these questions. And some of these questions are to reinforce the concepts, like what are the three main components of a function? So the body, the formal, and the environment in which it was defined, right? But I would also add the name. I think the name is important. That's the main thing we work with, right? The name, not necessarily the body. Or we also explicitly define the arguments of a function and the environment. We should be aware of it and aware of where the function is looking for these the variables that are defined either inside the function or outside of it. When does printing a function not show what environment it was created in? So for primitive functions and functions created in the global environment, they do not print their environment. So you'll see that tag towards the bottom of that, the print call. Like you can have a look at maybe, these are all base functions, right? So that should work, I guess. Print mean. Oh, I have my own. Let's remove mean from the global environment and try that again. So if you print the mean, it'll tell you what environment this function was defined. That's in the base namespace. So base is actually a package in R that gets built when R is installed. So when people say, I mainly use base R. That means that they're using the functions that are part of the base package. All right, so now let's look at function composition. So here this section is more of a style guideline, but it's useful to see how you can write a series of functions that are readable for future you, where if you come back to the functions that you wrote, you want to be able to make sense of them relatively easily and quickly. So there are a couple of ways to call multiple functions. And in this example, we want to create a square function. So that is x caret 2. And then a deviation function, which is x minus mean of x. So if you want to run those functions on a series of numbers, and so you'll see that you have to nest the function calls, right? So you deviate, use the deviation function first, then the square function, and then the mean, and then the square root, right, to get the standard deviation. So this is a little hard to read, right, because it looks like an onion, and you're reading from the inside to the outside. But R doesn't really care, right? It will just work with that. But for our purposes, we want it to be legible, and you want to sort of see the process from top to bottom. So you might want to write it like this. First, you calculate the deviation, then the square, then the mean, then the square root. And then the other way of doing this that's very popular in the tidyverse is to use the pipe operator from the Magrittr package. And you can first provide the series of numbers that we created with this run uniform, and then deviate, then square. And you would read this symbol as then, so deviation, then square those values, then mean, and then square root. That would give you the same result. So it's pretty stylistic, and there are different scenarios where you would use either style. So if you're not familiar with piping, this note here explains it. You have the left-hand side piped into the right-hand side. So if you're familiar with Linux pipes, this would be a similar concept. So this notation is equivalent to f of x, right? F function, running the function of f on x. And then if you have, so the left-hand side goes into the first position of the right-hand side. So this notation is equivalent to f x comma y. So there are strengths and weaknesses to each of these notations or styles. If you're nesting, it's pretty concise and well suited for short sequences. Yeah, so when I'm writing code, I try not to go over maybe 3 function calls that are nested. At most 3. Most of the time it's 2, because it does get hard to read, and sometimes it gets too long to fit in the width of my page. So it's better to break things up and show the steps from top to bottom. And you have these intermediate objects if you are writing code from top to bottom, as in the first example. It requires you to name intermediate objects, but it's not too bad. And sometimes the R code by its nature is sort of complicated, right? You have series of things that you need to do to your data set. So the intermediate object is just a side effect of those things that those functions that you're applying to the data. Piping is really nice to read, and I would recommend that for data analysis code, as Hadley says here. It's common in data analysis code, and it's great for operations that are expecting a specific input, say a data frame or a tibble, and are always returning a specific output that, say, a data frame or a tibble. So that's the strength of the piping, is that you can chain these operations and you expect the same class of output at every step. Any questions so far?
What are the differences between the native piping and the Magritte piping?
I think the implementation of the native pipe was, they tried to make it as close as possible to the Magritte pipe, but there are some technical differences. But I think they're replaceable. So if you write this notation with the native pipe, it should work. But yeah, it does have some quirks.
One thing I haven't figured out about the native pipe, and I just maybe haven't looked, but is the dot, how to feed the data into a something that's not the first position.
Yeah, I think it's the underscore.
Ah,
I guess I don't know, a function that would.
grep is one where it comes up,
Rep,
or grep.
grep. Maybe do like letters or.
Yeah.
So I think you have to name it and say underscore, and then provide a pattern. We'll say a, and I think that should work. Yeah.
Ah, cool. So it's just I wonder
Or
why underscore instead of dot.
Yeah, I don't know. Yeah. All right, so the other aspect of working with functions is this fancy term called lexicoscoping, and that's, in layman's term, is just being aware of where the objects that you're using are, essentially. And you might have an intuitive sense of what's what inside of a function. So here we're defining a variable x to have a value of 10, and then we're defining a function, right? Up to this point, nothing inside the function is evaluated, right? So we're just creating two objects in our environment, right? A function object and this x numeric scalar vector. It's when we run the function that R starts to evaluate the body of the function. So it will first do whatever it is inside of the function, and if it doesn't find anything inside the function, it looks outside of it. So inside the function, we are setting x to 20 and then returning x. So if you run this, you should expect a 20 as a output. So what are the rules that R uses to find and keep all of the variables in order, I guess? There are 4 primary rules. One is name masking, right? So we'll talk about what that means. Functions versus variables. A fresh start and dynamic lookup. So for name masking, it's referring to anything that gets defined inside of the function takes precedence when it comes to looking for any of those symbols as part of the body. So even if there are variables defined outside of it, like x is 10, y is 20, the variables defined inside of the function environment would get used. So maybe you can think of I guess name masking here refers to what variables like x here is masked because there's an x that is set inside of the function or defined inside of the function. So so it uses that 1 and 2 and gives you that vector of 1 and 2 rather than 10 and 20. If the name isn't defined inside of a function, then it starts to look 1 level up. So there could be multiple functions that are nested, but it will look 1 level up. In this case, that 1 level up in our example is the global environment. So it'll find that X that is missing inside of the body and use the 2 and give a 2-1 vector, right? If there is no X, right, it will just return an error and say that this function or X is not defined or something like that, that it's a familiar error. So that's what it does. It looks 1 level up. And this doesn't change the previous value of Y, right? Because Y is only set inside of the function environment, but there's another Y that is in the global environment that doesn't change. So that is the 20 that was defined up here, right? So if you call Y, it's going to give you that value of 20. Same rules apply if the function is defined inside of another function. So it looks in the current function, and then if it doesn't find it, it looks up. And if it doesn't find that variable, it keeps looking up. So this is the inner function, the I. And you have Z defined within the environment of I, and then you have X and Y. And so it'll look for X and Y. It goes 1 up. And I think it's probably looking for X first. So it will find it all the way in the global environment, and then y it's not in the environment of I, so it goes up and finds it in the G04 function, and then we'll give you the 1, 2, 3 vector. So those are some of the advantages of working with R, but there's some downsides, but it lets you conveniently find variables that were not defined in the function outside of it. So because everything in R is a function, so there has to be some way of finding symbols and variables inside of functions that is predictable.
So would you say, it seems to me like depending on the going one level up, if you're writing a program, seems okay if it's within a nested function, but once you go to the global environment or to attached packages, it sounds like a recipe for bugs.
Yeah, if you're writing a package function, you want to avoid any inspection of the global environment. And you want to keep all of the things that you want as inputs to the function within the function environment. Because there are ways to shoot yourself in the foot, as if anyone who's worked with R is quite well aware of. And what I tend to do is, or recommend, I always recommend that in the options for RStudio that you don't save any workspace data on exit. So I have this set to never, or restoring any R data into the workspace. So I avoid having objects sort of littered in my global environment, and avoid writing functions that would rely on objects that are in the global environment. All right, so just one minute, sorry.
While we wait, there's a difference between equal signs and assignments, like the arrow in functions, right? That makes a difference. That's a question for everyone. I remember there was something about that.
Inside of a function, you mean?
Yeah, about how you do assignment with the arrow versus the equal
Yeah,
sign.
generally we recommend against using the equal sign for assignment. It is an old feature of the R language that you would use equal sign for assignment, but it can be a little confusing to see multiple equal signs inside of a function, because mainly equal signs are for arguments. So they can be used, but we always recommend using the arrow to set. Yeah, but you can set a variable inside of the function, inside of a function call. And I think there are some examples below that have that, and I'll try to, we're out of time, so I didn't think this would take this, well, there's a lot of stuff to cover, so maybe we should stop there and have a discussion.
Yeah. In the like couple minutes that we have left, thank you for presenting, Marcel. Does anyone have any questions? Or any thoughts on functions?
So wonderful presentation, Marcel.
Thank you.
And it looks like the things you didn't get to, like lazy evaluation and dot, 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 those are actually pretty important, right? So,
Yeah, I guess we can come back next week and go through those,
yeah, I don't think
and
anyone
then,
signed up to present next week, so maybe we can just split this into 2 parts,
yeah,
if you don't
yeah, I did.
mind.
No, I don't mind. I
Okay,
really didn't time myself or anything, so I was pretty
that's,
unprepared.
that's fine.
Thanks, Marcel.
Yeah, thank you so much, Marcel.
Thank you.
So thank you everyone for attending. So come back next week where we'll do part 2 of functions. I'm learning a lot, so thank you again and have a nice weekend.
Thanks. See you.
Take care, everybody.